All right, geometry. Today we are jumping into the next section of Unit 7. So Section 1 had us look at polygons in general and more specifically their angles. The rest of this unit really focuses in on quadrilaterals. And the first quadrilateral we're going to look at is the parallelogram. Before we jump into that though, this unit has lots of vocab, which I warned you about, lots of definitions, and also lots of properties. So we need to look at the difference between the two. What is a definition and what is a property? So a definition is the least precise description that positively identifies an object. We do not want to get too specific here. If the description is not precise enough, then the definition could mean multiple different objects, and then we don't have a good definition at that point. However, if it's too precise, then we may be assuming things with the definition that we should be proving. So speaking of proving things, that's where we look at properties. A property of an object is something that can be proven by that object's definition, as well as combining that definition with some other theorems. Do not assume properties. Anything that is a property, we should be able to prove. So let's move along and look at parallelograms. Let's come up with a definition of a parallelogram, and then we're going to be able to come up with some pretty important properties of that parallelogram. So our definition of a parallelogram is going to be as follows. It's a quadrilateral, meaning it has four sides, in which both pairs of opposite sides are parallel. So this is our least specific definition. We have to have quadrilateral in there, or else we could be talking about anything really. But then our parallelogram happens when we have both pairs of opposite sides being parallel. Whoops. Okay, when we have this definition, we can prove some other properties, and we are going to do that. Our goal for the rest of the video is actually going to be to prove these properties, and then when you're in class next time, we will look at actually crunching some numbers. All right, property 1. In any parallelogram, opposite sides are congruent. Property 2. In any parallelogram, opposite angles are congruent. Property 3. In any parallelogram, consecutive angles are supplementary. And that one is pretty easy to prove just by the definitions of parallel lines and some of our properties that we've used there. And then our final property of parallelograms is that in any parallelogram, the diagonals bisect each other. Okay, here are our 4 properties, and now we're going to jump over to a blank page with a parallelogram on it, and we're going to go ahead and prove these. Okay, so here's our first couple. We're going to prove that the opposite sides are congruent, meaning that AB is congruent to CD and BC is congruent to DA. And we're also going to prove that the opposite angles are congruent. So we want to prove that A is congruent to C, and we want to prove that B is congruent to D. And we're actually going to be able to just kind of pump these together in the same proof because we're going to use congruent triangles. That's why we do all these congruent triangles in here. So the first thing I want to do is actually construct a diagonal. So we're going to make the diagonal from A to C, and what we're going to see is that we could have made the diagonal from B to D, but we're just going to make the assumption that if one diagonal creates 2 congruent triangles, the other one does also. So the specific term for that, if you ever get into any higher level proofs classes, is without loss of generality. So without loss of generality, we are going to construct diagonal AC. All right, so we're not going to do the most formal proof in the world here. In fact, I'm just going to start with our reason being given for this stuff up here. Maybe I'm going to draw a circle around it and put it down here. So the only given information that we have is the definition of the parallelogram. AB is parallel to CD, BC is parallel to DE. Okay, our next thing that we did was we constructed segment AC. And the reason that we're able to do that is by Euclid's axioms. It says that lines are a thing that exist. We can construct them. And now what we want to do is find some congruent angles. And we're able to do that because we have parallel lines. And parallel lines a lot of times come with congruent angles, especially when we draw this nice transversal in. So we're going to say that angle BAC is congruent to angle ACD. And similarly, we're going to say that angle DAC, I actually check that, I want to keep them in the same order. We're going to say that BCA is congruent to DAC. So let me make a copy here, and then we'll just change the letters. So BCA is congruent to DAC. So let me get some color in here. Our first line is saying that BAC is congruent to DCA. Our second line is saying that BCA is congruent to DAC. What's our reason for that? Okay, what we have here are alternate interior angles. We love them. All right, moving along, we need to say that AC is congruent to itself. So we can go ahead and punch in here that segment AC is congruent to segment CA by our good friend, the reflexive property. And we now have congruent triangles. So why are these two triangles congruent? So let's look here. We've got triangle, and I want to make sure I get these in the right order. We've got triangle ABC is congruent to triangle, it's going to be, let's see, CDA. Okay, so what is our reason here? Why are these triangles congruent? All right, hopefully you saw that we do have some angle-side angle congruence happening here. And now we're basically done. We can take these, everything that we want to prove here, and we can bring it down here, and our reason becomes corresponding parts of congruent triangles are congruent. So once we show that those two triangles are congruent, then all of our properties here, these opposite sides and these opposite angles are congruent. And if we want to get really super technical, then yes, I should do B and D, and then I should draw the other diagonal, and I can do A is congruent to C, but we're just saying without loss of generality here, if I prove one, the other is also going to work. Okay, moving along to the next proof. So that was property 1 and property 2. Now we're going to prove property 3, that consecutive angles are supplementary. And let's see, we've got our given here, so I'm just going to circle that and be lazy and go over here, and our reason for that is given. And then we are we're done. So yeah, we're done. This is not a hard one. So we can say that A and B are supplementary, and we can also say that A and D are supplementary. Because they are what type of angles? These are same side interior angles, and we had the parallel lines. And we're done. Proof over. Parallel lines gave us those consecutive supplementary angles. All right, now we're on to prove property 4, that the diagonals bisect each other, and we're going to use actually some of the properties from above, or at least one of them. So first off, we've got our given right here. And our only given is that the lines are parallel, the opposite lines are parallel. And then we're actually going to use a property from above. We're going to say that AB is congruent to CD. So we've got segment AB is congruent to segment CD. And our reason is something that we just proved. Opposite sides of a parallelogram are congruent. So this is kind of why we prove these properties, because then we can use them again. All right, now we're going to find a couple angles. So we're going to use angle BAE, and angle BAE is going to be congruent to angle DCE, so I'm scrolling up so you can see that a little bit better. So BAE and DCE, and let me draw those in. And then we're going to do the same thing with angle ABE and angle CDE. And I may as well mark these congruent since we already showed that. Okay, so we've got angle BAE is congruent to angle DCE. And we're going to do the same thing with some other letters. We're going to have angle ABE be congruent to angle CDE. Our reason for both of these is the same though. What is it? All right, we have alternate interior angles. Which means we now have congruent triangles. So let's go ahead and say that this top triangle up here, this one right here, is congruent to this bottom triangle here. So that is triangle ABE is congruent to triangle, let's see, that's got to be CDE. And our reason for that is, all right, we've got angle side angle again. And now we're basically done. So with those two triangles being congruent, we can say that segment AE is congruent to segment EC. We can also say that segment BE is congruent to ED. And our reason for that is our good friend, corresponding parts of congruent triangles are congruent. And then what that means is that the diagonals bisect each other. And that's by the definition of bisect. Okay, that's all I've got for this video. We've just proven a whole lot of stuff about parallelograms. We're going to use these proofs going forward as we look at things like rectangles and rhombuses and squares. So all of these parallelogram properties kind of stay in play. They're important to remember. And then we'll work on crunching some numbers in class tomorrow. So I'll see you then.